Ever wondered if you can add two numbers without using the plus or operators? That's exactly what sum of two integers asks. This Pattern Mastery 100 favorite is a fun twist that shows up in both coding interviews and low-level systems work at top companies. If you can master bitwise addition, you'll prove you have a deep understanding of how computers really calculate, and that gives you a major edge. Let's break it down. You're given two integers, a and b, and need to return their sum, but you can't use the plus or minus operators. You must use bitwise operations like AND, XOR, and shift. Now let's assess. Normally, addition works by summing each bit, carrying over when needed. Bitwise XOR adds without carrying, while AND plus left shift finds where carries are needed. The trick is to loop, add with XOR, then carry with AND or shift, until there are no more carries. This simulates how a CPU adds numbers at the bit level. Here's our approach. While b, the carry, is not 0, we use a XOR b to add the bits, without including the carry. Then, we use a and b, left shifted by 1, to find the carry and move it one position left. Next, we update the values of a and b with these new results. Once the carry becomes 0, a holds the final answer. Let's try to implement it using solution 1. Here we're defining a class called solution. In Java, every method needs to live inside a class, so this is just the container that will hold our function. Think of it as the name of the toolbox that holds our tools. This line declares a method called getSum that returns an int, a whole number. It takes two integers, a and b, as inputs. You can think of a and b as the two numbers we want to add together, but we're going to do it without using the plus operator, just using bit operations. Here we define two constants. Mask equals 0xFFFFFFF is a 32-bit mask where all bits are 1. In binary, this is like 1111, 1111, 32 ones. We'll use this to make sure our calculations stay within 32 bits, just like regular Java ints. int_max equals 0 by 7 FFFFFF is the largest positive 32-bit integer, 2,147,483,647. We'll use this later to decide if the final result should be treated as a positive or negative number. This line starts a loop that will keep running as long as b is not 0. The idea of the algorithm is: a will hold the partial sum, without the carry. b will hold the carry that we still need to add. So while there's still some carry left in b, we keep looping and adding it in. Now we update it to be the partial sum without the carry. AB uses the bitwise XOR operator. XOR acts like add without carrying. If the bits are different, 0 and 1, or 1 and 0, the result is 1. If the bits are the same, 0 and 0, or 1 and 1, the result is 0. This gives us what the sum would look like if we pretended there were no carries at all. Again, and mask keeps the result in 32 bits. So, this line is, let's compute the raw sum of a and b ignoring carries, and store that back in a. Now we update b to be the new carry. Carry 1 means we shift the carry 1 bit to the left. This is like saying, the carry from the 1's position should be added into the 2's position. The carry from the 2's position should be added into the 4's position, and so on. Again, and mask keeps everything inside 32 bits. In everyday terms, we take the carry we computed and move it into the position where it should be added next. This closes the while loop. By the time we exit this loop, there is no more carry left, b is 0, and a contains the final 32-bit result of adding the original two numbers using only bit operations. This line returns the final answer, but with a small twist to correctly handle negative numbers. First, we check a less than equals int_max. If this is true, a is within the range of a normal non-negative 32-bit integer, so we can just return it directly. Otherwise, a represents a negative number in 2's complement form. To convert it to Java's signed int, we do a mask which flips all the bits of a, and then tilde, flips them again. Combined with how Java treats integers, this expression effectively interprets a as a proper negative number. Overall, this whole function still runs in O1 time and uses O1 extra space. And that's how this algorithm works. It first sets up bit masks and limits so we can safely work with 32-bit integers, then repeatedly combines the sum and the carry using bitwise operations until no carry is left, finally adjusting the result to handle negative numbers correctly. Solution 1. Test case 1. Let's test our function using this simple input pair. A equals 1 and b equals 2. These two numbers are the values we want to add together using our bit manipulation approach instead of the normal plus operator. In binary, the number 1 is 01 and 2 is 10. There are no overlapping 1 bits, which means no carry is generated on the first step. So the XOR step gives us 0110 equals 11, which is the binary form of 3. Since no carry remains, the algorithm stops and returns that result. And that's exactly what our program outputs, 3. And the expected result is also 3, so the test case passes perfectly. Our implementation handled the addition correctly without ever using the plus operator. So, our implementation is correct. The algorithm successfully computes the sum using bitwise operations, efficient, accurate, and fully aligned with the expected output. Now let's try another implement approach using solution 2. Here we're defining a class called solution. In Java terms, this is just the container that holds our method. You can think of it like naming a folder where we keep our getSum function. This line declares a method called getSum that returns an integer. It takes two integers, a and b, which are the two numbers we want to add. But again, we're going to do it without using the plus operator. This version, solution 2, does the same logic as before but in a more compact, recursive way. Here we define two constants that help us manage how numbers behave at the bit level. Mask equals 0xFFFFFFF represents 32 bits all set to 1. It's like a filter that keeps our numbers within 32-bit integer limits. int_max equals 0 by 7 FFFFFF is the largest positive 32-bit integer. In plain language, mask makes sure we stay in 32-bit land, and int_max helps us decide if the result at the end should be treated as positive or negative. This line is the base case of our recursive approach. We check if b equals 0. That means there is no more carry left to add. At that point, already holds the full sum. If b is 0, we immediately return the final result, but we handle two situations. If a less than equals int_max, then a fits in the normal positive integer range, so we just return a. Otherwise, a represents a negative number in 2's complement form. The expression tilde mask adjusts the bit so Java interprets it correctly as a negative integer. This is the heart of solution 2, the recursive call. Let's break it down. AB uses XOR to compute the partial sum without carries. AB and mask keeps that partial sum within 32 bits. This becomes the new A. A and B uses and to find where both bits are 1. Those positions are where a carry should happen. A and B. 1 shifts the carry 1 bit to the left, moving each carry into the position where it should be added next time. A and B, 1, and mask again keeps the carry within 32 bits. We keep calling getSum until eventually the carry b becomes 0, which triggers the base case we just saw. And that's how this algorithm works. It first sets up constants to safely handle 32-bit integers and detect positive versus negative results, then uses recursion to repeatedly combine the XOR-based sum and the shifted carry until no carry remains. Efficient, simple, and elegant. Solution 2. Test case 2. Let's test our function using this input. 2 and 3. These numbers represent the two values we want to add together using our bitwise addition approach, no normal plus operator involved. Here's why the solution works. We're simulating addition using XOR and carry operations. For example, in binary, 2 is 10 and 3 is 11. XOR gives us the sum without carry. 10 11 equals 01, which is 1, and gives us the carry bits. 10 and 11 equals 10, which is 2, and then we shift that carry left to become 100, which is 4. We then repeat the process with 1 and 4, and the final combined result becomes 5. The recursion stops when no carry remains. And that's exactly what our program outputs, 5. And the expected result is also 5, so the test case passes with flying colors. So, our implementation is correct. The algorithm successfully computes the sum using pure bitwise logic, efficient, accurate, and reliable. To wrap it up, this was a classic bitwise logic problem that pushed us to think beyond basic arithmetic operations. Breakdown recap. We started with two numbers, a and b, and needed to find their sum without using the plus or operators. The key idea was to use bitwise operations to simulate how addition happens at the binary level. Assess recap. We broke it down conceptually. XOR handles addition without carry, while and combined with a left shift identifies where carries occur. By repeatedly applying these operations, we could perform addition just like a CPU does internally. Structure recap. The logic was simple but powerful. Loop until there are no more carries. In each iteration, XOR adds the bits, and plus shift finds the carry, and the values update until completion. Implement recap. We implemented the solution in LeetCode, and it ran successfully without errors. Check recap. After testing with different inputs, the code passed all test cases. confirming that our bitwise approach worked perfectly. The key takeaway? Even something as basic as addition can be reimagined with pure logic. Problems like this remind us how powerful and elegant bitwise operations can be when we truly understand what's happening under the hood.